Let us now walk through the simulation process by the equation-based simulation in Octave. First, I will go into the work folder. So in the work folder, it is empty. Let me create a new folder. So I will give the name as the topic which we want to simulate. Let us say it's an RLC circuit. So it's a RLC. So remember that for every circuit or every project, you have to create a folder. And within the folder, you have to have two important files. I will paste them. These are templates. I'm including the templates in the resources section of the course. The names of these two files, model.m and sim.m, the names also should not be changed. Every circuit or every project that you are going to simulate, in that folder you will have these two important files, sim.m and model.m. And within the model.m, you will be writing the system model, whichever you want to simulate. The sim.m file is actually the main script file which will actually run the simulation and call the model.m. So this is basically the concept. So let us see what goes into these two files. So I will open both sim.m and also model.m. So both these are open. I will kind of separate them, so you can see side by side. So the main sim.m file, so you can just go through this script. It's pretty easy to understand. Clear all variables, clear screen. Then you have two important parameters you need to enter depending upon your application. So this is step time. Here I have given a default value of 1 e to the power of minus 6 or 1 microsecond. T final, I have given a default value of 100 millisecond. You are free to change it according to the application. This is the end time. Resume is equal to 0. Set it at default value. I will explain later what this means. Do not touch this for now. Now there are 3 more lines here, statements. These are mainly for displaying in the plots. Display colors. When you have several multiple plots on the plot window, you can choose the color sequence. K for black, blue, red, green, cyan. K is again black and magenta. So you can sequence them in any order that you want, and you can put how many ever you want. It will take it will appropriately take the first valid number of colors in the sequence. This statement, state vars, state variables, that's what it means, and that is given a variable name x, and scope vars are given a variable name y. You just don't need to worry about these aspects till you get to know more about it and you become experts and you want to manipulate it. Till that time, you can just leave it as it is. So which means that for every for getting started, for every simulation, all you need to do is these two values you need to adjust: time step and final time. Finally, OctSim, which is one of the files that will be called which we had installed after downloading lu helpers tar.gz file. This will run the simulation and plot and display the results to you. So this is the sim file. The sim file is absolute must. This is the main simulation script file. Sim is what you will go into that folder, project folder, and run sim. So within Octsim will execute model file, whatever is there in that directory. So in that directory, the model file that you would have would probably represent the circuit or whatever system you are trying to simulate. So this has a template format like this. Do not change this. I am enclosing both these templates in the resource section of the course. You can download it and then use it as your starting file, and then type in the model for each specific circuit. So the first line is function, and for all the simulations, this is the format. X dot is equal to model, parameters that you are passing, x, which is the state variables, t, time, params, if there are any parameters to be passed. You can have some comments here. You need to place this command here. Do not disturb it. Let it be there. And then between these two lines is where you will type in the dynamic model equations of your system. So this is where the system equations will come in there. Then after that, there is something here called scope it. So you can use this for scoping variables. See, state variables in the simulation, in the sim.m file, the display of state variables is automatically taken care of by this statement. But any other variables that you intend to see, which is part of your system model, then you need to scope it in this statement. So scope it is just like a probe scope, and you can probe at any number of variables within the file, and you will be displayed the appropriate waveform for that variable. So it is like this, scope it, and then within this array you can give a list of variables. For example, some vs comma v0, something like that one. So this is the model.m file. These two files must be there, and in most of the cases these two files are sufficient. But as you go to advanced simulations, you may need to attach few more files. For example, if the models become complicated, in this section you may call other functions, so therefore you may need those functions also. But for now, do not worry too much about that. So let us now get on with the simulation and take an example and see how to incorporate the equations here. So for that, first let us look at the circuit and understand what are the dynamic equations for an RLC circuit, and then place that accordingly in this section, the model section. Sim.m, you don't need to edit much. We will come back later and then see if we need to edit this. Otherwise, we can leave it at this for start now. Let us now draw the RLC circuit and try to understand the equations that come out of that. So it consists of a source R in series with L, and then a C as shown, the capacitance, and then across the capacitor let us have a resistance. So this would be the basic RLC circuit. Now let us name the various component parts. We will, for the source, let us give one single pulse to initiate the oscillation. We'll call that one as Vs, V source. This resistance here, we will call this as R1. This is L. This we give a symbol C. And this we will call R2. And the voltage across R2 or voltage across C are the same, and this will be Vc. Now these are the variables that we have fixed for the circuit, and now let us write down the equations that represent this circuit. So now first let us say that a current IL is flowing through the inductor. So inductor current is one state variable. Always the variable associated with energy storage are considered as state variables. IL is inductor current, which is a state variable. Voltage across the capacitance is also a state variable. So if you consider IL and write the equation of the voltage across the inductor using Kirchhoff's law, so you will get L dIL by dt. L di by dt is the voltage across the inductor here, which is, if you take this loop, this voltage minus the voltage drop across R1 minus Vc, which is the voltage across the capacitance. So let us write that down. So L dIL by dt is nothing but Vs minus drop across R1, which means the current flowing through R1 is same as current flowing through L, which is IL into R1. So that is the drop across R1 minus Vc. At this node the potential is Vc, so I am going to write it as Vc. So this gives you the first equation with respect to the state variable IL. Now let us take the other state variable, which is the voltage across the capacitance C. So C dVc by dt is nothing but the current that is flowing through the capacitance C, and that is equal to the current at this node IL minus the current here, which goes out here, which is basically the current of R2, will be the current that flows through C. This is by KCL. So the current through R2 is nothing but Vc by R2. So we can just write it down. IL minus Vc by R2 will be C dVc by dt. So this represents, these two equations, dynamic equations, represent this RLC circuit completely, along with the input voltage spec. So state vector X is nothing but IL and Vc. So these are the state variables. So using this equation, we should now be able to simulate this representative RLC circuit in equation form using the Octave simulation package that we just installed. So let us try doing that. Now open the model.m template file, and in the template file, in the space here provided for typing in the dynamic equations, we shall type in the dynamic equation of the RLC circuit that we just now derived. So first let us put in equation 1. Equation 1, where LIL dot is equal to Vs minus IL into R1 minus Vc. So I have taken L on this side, so therefore divide by L. So this is equation 1. Now the second equation, CVC dot was IL minus VC by R2. So again I have taken C to the right hand side. So you have only the VC dot on the left hand side. So this is equation 2. Now these two equations fully represent the RLC circuit. Now what next? Look at the function. X dot here is the output parameter. We have to set X dot as the output parameter. So we have to include that statement. X dot is equal to a vector which is IL dot and VC dot, like this. So now this is the output variable which is passed out of the function. What is coming into the function? X and t. So X is the state variable. We need to assign it to a variable for this particular problem. So X1 is assigned to IL, generic value X2 is assigned to VC state. So now the parameter coming in, X, is assigned to proper state variables and the equations are computed and the dot values, the derivative values, are passed out of the function. So this is how the model gets computed every time step. Then in order to complete this, we need to give values for R1, L, C, R2 for the computation to progress. Now let me give some arbitrary values for now. I am setting L as 10 millihenries, R1 as 1 ohm, it's a series resistance, C as 100 microfarad, R2 as 1000 ohms. So this will set the parameters of the component. Now what about the source? Source, we said we will give one single pulse to initiate the start of the resonant oscillation, decaying resonant oscillation. So Vs, we will, because this is octave, it is very powerful, you can do it in this fashion. Yeah, Vs. What does this mean? First just look at this. T greater than 10 milliseconds. T greater than 10 milliseconds, which means this will be logic 1 for T greater than 10 milliseconds. Consider this aspect here, T less than 60 milliseconds. This will be logic 1 for T less than 60 milliseconds. Now there is an AND function in between. So this A and B would give you T greater than, so this whole thing which within the bracket will be 1 when T is greater than 10 milliseconds and T is less than 60 milliseconds. So between 10 and 60 milliseconds, this part within the bracket would be, within the parenthesis, would be logic 1 into 10, it will be a 10 volt. So you will get a 10 volt pulse. So this is how we set the input for this particular case. And that's it, it is complete, the file is complete. We save it and then start the simulation and see what happens to the waveforms. I have moved the model.m file to the left. I will now open the octave. I will clear up the octave command window. So before you run the simulation, we have to first move into the directory where this particular model.m and sim.mr. So we know that it is in the work directory cd work directory. You see already it shows up RLC. So let us change directory into that cd RLC. So you see that there is a model.m and sim. Model.m, I have shown it here alongside for you. Sim is already also here. Sim is set at 1 microsecond step time and 100 millisecond end time. So, and when you are opening Octave for the first time only, when you run this package load lu helper sim. So now the simulation helpers are loaded and ready to help you. This command you have to run every time you open Octave afresh, but you have to load it only once in a session. So now let us run the simulation. We run sim. So on running the simulation, after executing the simulation, you will see the plot window, and the plot window you see two waveforms here. One is the blue waveform and the black waveform. Now let me pull the plot window onto the side here, and here let me open. Yeah, before I open, let me see, have a look at the model.m file. IL and VC, these are the state variables, and what is being plotted is the state variables. So if you look at the sim.m, state vars x, these are the variables that are plotted, and we know that x is IL and VC, and the first one IL is black, the second state variable VC is blue. So we can make out from here that the blue here is the underdamped oscillation, and the blue waveform is the voltage VC across the capacitance, and the waveform in black is the current through the inductor. Now these waveforms, of course, you can zoom in and zoom out at will. You can use Z plus and zoom into portions of the waveform and make your analysis, study the waveform and the values. Let us say if we also want to see the input waveform Vs, what do we do? So let me close this and go to the model file. We would like to say see this variable. This variable is Vs, is not a state variable, but still we would like to probe it. So in order to do that, we have this function scope it. So you scope Vs. I uncomment it and I will put in the array Vs as one of the variables to see. Save that, and then you can re-execute sim, and you will see that the third variable now appears, and the third variable, which is in red color, is the input variable Vs. Now this is good enough, but I would also like to label these various waveforms. How do I go about doing that? So let me close this. Let me go into sim. See here, this is the display colors. This is actually in if you go and read the Octave manual and read the plot syntax. I can have two colons, semicolons, and within the semicolon, let us say I can give any label, IL. The first one was IL. And let us say I go to B. Within that quotes, I will, within the semicolon, I will put the next, VC, and the third one, red. Within the quotes, I will include the label for VS. So you will see that the labels will also get plotted, and it will identify for which color. So let us save this and re-execute the script. So running sim again. So now you see that I will make it big. So you have the three waveforms. First one black, IL. So you have IL. The next one is the blue voltage waveform, VC, blue, and the red waveform, the input waveform, VS. So you will get a label like that. Now this becomes a complete documentable plot that you can use for your further documentation and saving and printouts.